All right, we're going to go ahead and get started. I just want to share a couple things before we start the broadcast. Can you see the slide that I'm just posting here?
Yep.
All right, so just a couple reminders for those of you that are tuned in. A couple of new activities for the SIG HPC education chapter. We are reactivating our blog post. There is a new blog post there, and we hope to have others coming in the near future, so we want to redirect you to that. We also have now started Facebook and LinkedIn groups, and so we will have notifications there of various things. I've given you the link to our website, and it will have the link to the blog, and we'll also post the addresses of the social media there if you'd like to join us that way. Then before we get started, note that this particular broadcast does not have a question and answer page, so we have this chat application, which I'll show you again at the end, but it's basically SIG HPC Education Hosting, acm.org, called AJAX Chat, and you can sign in with your name or nickname in parentheses, and we will hold the questions until the end of the broadcast. And unfortunately, AJAX Chat's been going up and down the last 30 minutes, so I'm keeping my fingers crossed that they're not doing maintenance at ACM. But in case they do, the fallback is to send me an email questions, and we'll come back to that at the end if necessary. So those are my words by way of introduction. And so now what I'd like to do is introduce our speaker, Dan Garcia from University of California, Berkeley. And Dan, I'll let you go ahead and start your presentation.
Thank you so much, Steve. Delighted to be here, folks. I have a slide deck that I can start with, so I don't know if we want to just jump right in, but I'm Dan Garcia, teaching professor at UC Berkeley, as Steve mentioned. I've been member of ACM for many, many years, been part of the CS Principles movement, the CS for All movement, whose goal is to reach students who are not normally getting computer science. And have created a course, co-created a course called The Beauty and Joy of Computing. And let me just jump right in and get my slide deck going here. And I'll put it here, and bloom, and bloom, and bloop. Okay, so I hope this is, let me go here and go here, yoink. All right, can you guys see my slides? Perfect. So this is going to be a talk about how we're bringing HPC Big Ideas to high school students and learners everywhere. We have created, as I mentioned, this Beauty and Joy of Computing course that has a MOOC, and so that's the kind of worldwide part of it. We'll talk a little bit more of that, and we'll also talk about some of the HPC Big Ideas we share in that. So let's just jump right in. So lest you think that I'm the only one who's part of this family, there's a whole family of us who are creating the curriculum and editing the curriculum and sharing this with many teachers worldwide. Brian and Harvey and I at Berkeley founded the course. Tiffany Barnes joined very shortly thereafter, worked with some outstanding grad students and some outstanding high school teachers and others to continue working on this course. EDC is a particular group in Waltham, Massachusetts, who is helping polish this course and make it more high school friendly. So many of you know that computer science is not very visible in the high schools. This is the number, by one measure, is the number of high school students of 2012, it's a little dated, but who are taking different various AP courses. You see that the folks who are taking history and English and science are roughly around 1 million, and computer science is down here in the 20 to 40,000 range. And even more so, more egregious is how underrepresented our computer science course AP is. With only 50% being young girls and 8% being folks of color. So we need to bring computer science to more high schools and make it more visible. So this is the kind of the pitch for why CS Principles exists, computer literacy of the 21st century, but AP is only available in very few percent of the schools. So there was a vision by CuNi, who is an NSF program manager, to create a new course called computer science principles. She worked with the College Board and Lynn Diaz and lots of folks, Owen Astrachan, Amy Briggs, to get an NSF grant to make that a reality. So we've been developing this course for almost 4 years. It's engaging, accessible, inspiring, rigorous. It is a course that in theory would sit in front of CSA. CSA is modeling what happens in your CS1 course, and CS Principles might model what happens in your non-majors course at university. So let me just show you a quick video that will explain what CS Principles is about. I have this all queued up here. So let me go here, and hopefully you guys are hearing this.
No, we're not getting the audio.
Not getting the audio. Okay, well, thank you for letting me know about that. This is I'll share the URL and I'll just summarize it. This is an interview with many teachers talking about how computers have transformed the world, and how many teachers are using this across the country to inspire young students. As interviews with students, we're talking about how this course is so inspiring to them, and if only more classes were like this, more young girls would go into computer science. And this is Art Lopez talking about this course teaches you how to think. I've watched this video a couple times. The course is empowering. Yeah, and creative thinkers are wanted to be part of that. So thank you for that. Good to know that that didn't work. Let's jump right back here. So here's the URL, YouTube, and this little. I can share these slides with you later. I'll leave it up for a second so people who are watching this can copy or paste that in. So the idea behind CS Principles was to have a framework that's defined by some big ideas and some computational thinking practices, not to tell teachers you need to teach exactly this on day 14, but to provide an overview for kind of the principles, the framework that has to go into that. So this is the csprinciples.org contains this. So computing is creative, abstraction, data and information facilitate knowledge. Here's a place where some HPC Big Ideas are applied as you're needing to process that data. Certainly algorithms, developing computational solutions to computational problems, programming, kind of how the internet works as part of that. This used to be systems, and that was a place where quite a few HPC ideas could have gotten shuttled into. It transformed into the internet, and so it's a little bit harder to shuttle those ideas in. Systems was deemed too ambiguous. People know what a system was, from a low-level system, from an embedded system to a large multi-machine system. And the global impact of computing is really important as well. And there are these 6 computational thinking practices that define the framework. So it's kind of balanced between the big ideas are the big ideas are the facts that you know, and the practices are what you do. So these are the verbs in some sense of what will happen in class. Connecting computing, developing artifacts, abstracting, analyzing these artifacts, communicating, and collaborating. So this is a very high-level framework, and then curriculum designers can create any course they want around that framework. So here's the example. It's inspiring and innovative in many ways, in addition to just to being more than just the old way of doing computer science, but maybe lighter. If you can imagine doing this course very poorly, in which you say, well, let's just do what they do in CS1, but do it slower, and maybe stop halfway in. And that's what many people do in their non-majors course. That's in fact what we did in our majors course 10 years ago, before we kind of awoke to the reality of providing more perspective of what non-majors should learn. So the old way of assessing CS exams has been a big 3-hour exam. And this year, and through Principles this year and going forward, there are going to be 2 performance tasks. So this is just kind of ways that the students get assessed. They do have an exam. It's a little lighter weight, 2 hours versus 3, but they have creating code and doing some research on a computing innovation that they're passionate about. So this is just ways that they're assessing the exam. Here's an example of the framework, very high-level framework. You can think of these as like chapters and sub-chapters, and then sub-chapters and pieces of that. So these are the four kind of subcategories of this Principles framework. Here is the document. Here's a book. If you ever get the book, it's called The Purple Book. So within the Big Idea 7, which is global impact, you might have 7.1. This is kind of the way that you talk about global impact. And then as the students understand these ideas, learning objective students will be able to do these things. This is kind of, again, the verb coming in here. And these are the facts. These are just some facts that the students will need to know and may be quizzed upon at the end of the year. So the idea behind CS Principles was, we have to not, this is Jan CuNi's idea. CS 10K was her effort that she instilled and launched, say, 2008. So this is 8 years ago. Is that, you create this wonderful course, and then you have to get amazing high school teachers engaged and prepared high school teachers to teach this course. So this is one of our PD sessions. There's me in the middle, and there's the teachers that we worked with who we flew into Berkeley. Perfect. Okay, so this is part of the Jan CuNi's vision to bring CS Principle courses to 10,000 high school teachers across the country. So what differentiates BJC from other principles efforts? As I mentioned, the curriculum framework allows for curriculum developers to have some flexibility for what they design for these courses. So this is, we take a more programming heavy approach than other courses. We use this graphic language that makes these difficult questions, difficult coding ideas easier, certainly. It's a blocks-based language. We teach the principles of recursion, procedures as data, or Lambda. Again, some people don't even get Lambda until they get to a junior level course in college, and so we're doing this early. And concurrency distributed computing, certainly as HPC ideas. We use the language Snap, which came from BYOB, which came from Scratch. So we were looking around the space of blocks-based languages and saw Alice and App Inventor, and eventually settled on Scratch, but realized Scratch had a wonderful design, but didn't have any students writing functions. And if you couldn't write a function, you can't use abstraction in the way that we think of it. So what we did is we had a programmer, Jens Monig, who had a version of Scratch that he had created called Build Your Own Blocks, BYOB. And we then rewrote that in Snap in JavaScript. And so I show this picture of the iPad to show that we can now have mobile apps very easily, because you just bring up a web page and you load in your Snap browser, load Snap in your browser, and you've got your mobile app action. This is an example of writing a for loop and then calling it in a language. And I challenge many people to look at the languages they use, and can you, if for loops didn't come prepackaged with your language, could you just write a for loop and naturally use it? And most languages can't do that. So Snap can. So that's a nice feature there. So here's one of the here's one of the reasons. This is a slide from lecture of why we teach procedures. If you look at a student's piece of code and they have these 3 blocks, I'll just quickly tell you what these do. I put a pen down and I repeat the following thing 4 times. I move and I turn 90 degrees. You'll see that this is going to draw a square of side 25. And I look at this piece of code, I say, oh, wow, this is the same kind of thing. And the student has this also in their program. And this is drawing a square of side 100. And you're seeing them do the same thing here, a square of side 395. And you say, wait, shouldn't you use abstraction here and kind of collapse these into one? And so the idea is, yes, you should. You should write the draw square of side routine. This is a command block because it's going to do something. So the shape of the block indicates that. The shape of the block is like a puzzle piece. They fit together nicely. This is an input, a length. I'm going to drag this down here to drop it into that slot. And that then says this input is being fed into this move block. And then when I call it size 100, the number 100 gets passed into this input, and then the formal parameter gets assigned to that value, and then it's used here. So this is how I can now generalize this to the draw square procedure. And everyone usually in the CS Principles family and the CS family nods, harumph, harumph, harumph. We agree this is a nice thing you should teach students. And then I talk about why you should use functions. This is, again, from this functions lecture. Generalization, building blocks of our program. You can compose them together. This is an example of not a command block, but a reporter block in Snap. And this is the idea of, if I want to figure out the difference between our ages, I might have this block. Me might be an abstraction. I have no idea what me and you are, other than they represent the 2 of us, 2 different people. They might be a very complicated database record. There might just be a simple set of numbers. I don't know how we're going to represent, but I don't care. That's beautiful abstraction. Birthday, somehow able to go to that me and query that and say, all right, return the birthday in whatever format birthday returns. Again, I don't care. It could be on the day of our Lord, blah, 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 or it could be 2010 dash dash for a young person. Then I have a block called birthday to days since 1900. This assumes people aren't born before 1900. which is a pretty reasonable assumption nowadays. And so this might return the total number of days since 1900. Now, that gets fed into those two get fed into the subtract block, and that's now the difference of those days. That might be a negative number depending on who's older. If I pass that into the absolute value block, that then figures out the actual distance between that in terms of days. And if I divide that by 365, roughly, I get the number of years we are apart. So this is an example of doing a pretty complex calculation, but there's not a single for loop here. There's not a single iteration. This is just one nested compound expression. That's what's kind of beautiful. So that's the second reason we use functions. And the third, and this slide hopefully makes some HPC folks happy, is that we tell them that if they can live with a functional paradigm, not an imperative sequential paradigm, but if they can live in a functional paradigm, then it really makes controlling a data center possible. If you can think about wrapping what you want to do in that functional paradigm, again, that has no side effects. We talk about what functions do. Pure functions have no side effects and no state, and the output is purely, the singular output is purely a function of the inputs, which may be many and maybe none. Then these functions can then be parallelized really trivially because there's no state. It doesn't matter the order that these things get processed. So it lets a system that were to then distribute your workload among many computers, many helper machines, and then gather that value back. The order of operations doesn't matter, and thus we can parallelize that pretty easily. So here's an example of why we talk about functions. And then we actually share this. This is a cut from several different lectures. So I don't go in order like this. This is a little bit too fast for the students, but I'm cutting and pasting into this PowerPoint slide deck to just kind of show you what the big ideas we're doing. So a second ago, you saw 3 different cases of trying to draw squares, and you said, boy, why isn't that collapsed into one block? Well, here's an example of 3 different clusters. The top draws a normal square you've seen before. Again, we're going to hard code the number 100 here. The second draws a dashed line square, and the third draws a wiggly line square. And you say, well, Dan, before, the only thing that was different was the value passed into the side of the square. Well, if you notice, the only thing that's different here is the green command block that tells you how to draw a line. So shouldn't you be able to collapse these into one general block? And because functions as data is something we teach our students and supported by our programming language, we certainly do. And so many people in their language that they're using don't support functions as data in the language, so they don't teach it in the class. But fortunately, Snap does, and so we teach it in our class. And here's an example of how this is done visually. So before, you remember this, the orange input was how we fed in the value 100 or 25 or 395. Well, here, this is our formal parameter line drawer function. Now, Snap actually puts a little lambda to remind you this is going to be a function that's going to be called in, that's going to be passed in. And this also means that the block itself has a gray border around it. And we'll talk about that in a second, but the gray border is Snap's way of saying, don't evaluate this right now, kind of thunkify it so that you pass the function in without actually calling draw wiggly line right now. It's going to call wiggly line later. When is it called? Well, whenever this gets run. So this, again, this looks like all the pattern of these 3 things. Repeat for run the line drawer program with inputs 100. So here we're hard coding 100 because that isn't the point of this. But the idea is this line drawer function can be passed in real time. And draw wiggly line happens to be one that we've predefined. But you, again, just like an anonymous function, you could make a draw drunken walk line without even giving it a name and passing it in, and it would still work in a beautiful way. So this is a kind of a clean way that we in Snap continue the idea of abstraction with the idea that functions can be data, and then we can abstract the function you're passing in, not just abstracting the number you're passing in. We then use this in one of the most delightful demos I've seen to teach recursion. This is a V demo. And here's the V function. I don't want to dwell on this because this is really about recursion. But part of the idea is because functions are first class in our language, we can make a list of them. This is how you make a list of things. This kind of visual sense is to make a list. And if you notice, what is it making a list of? I'm making a list of functions. Square is a function that will move the sprite around seamlessly as in a square pattern. This will move it around in a hex pattern. This will move around a star pattern. this V will draw V. And so the powerful idea of this is what happens if you then pass V in as one of the functions that it might run. So V is going to do this thing where it turns to the left and then runs one of these things from shapes. And shapes is this global list that has a list of functions. It just runs one of them. So you saw that run before a moment ago with running. And if I click this arrow, you can pass an input to this. These guys don't take any inputs. But this is this wonderful data teach recursion where V can choose V. And so you get this beautiful pattern of a tree here. So maybe this is appropriate time to kind of stop and jump out of my slideshow and show you a demo of how we do some of these ideas. So let me pull out of this and then jump back over here to my Snap. So this is Snap. This is a graphical language. It runs in a browser. I have loaded the tools, which allow me to bring in some of the powerful tools that HPC folks are, I'm sure, used to. Here's Map. Here's Keep and Combine. So let's just give you a quick demo of how we use those in our course. So we make a list visually, so I can grab the list block and then make a list of a couple things. So let's make a list of one. Let's make a list of one. Whoops, clicking the tab button here. 1, 2, and oh, maybe I shouldn't use tab on Safari. That's very good. And 10 here. So if I click this, you'll see that I'm making a list of 1, 2, 10. And what I often do when I'm doing this, a demo with students, is I often, and I'll do this in workshops as well, is I'll say, all right, and this is often a workshop for students who program before, and that's not a workshop for non-programmers. I'll say, using any language you want to, I'd like to write a program to double salaries. If this is the amount of money I'm giving to my employees, let's say this is 1,000, 2,000, and 10,000 for some, let's say 3 part-time workers for my company, and I want to write a program to double their salaries. So let's just do it quickly. I'll say let's make a block, and let's say double salaries here, double salaries. It's going to take in an input of salaries, and it's going to be a reporter. It's going to return those salaries. Let's do it quickly. This is how most students do write this. So to make the double salaries block, well, I probably need to have, let's see, an answer, which I'm going to be filling up here. I'm going to be filling up a list. So I'll say the answer, and I maybe initialize this to the empty list because we're going to be processing that list of salaries. So set answer to the empty list here. This is a typical way students do it. I'll just do this quickly to this. And now I'm going to use the for each loop. This is, most people do this way, the for each, and I can rename this for each salary of salaries. Notice I'm grabbing this, and this is very much like the I mentioned before how you can grab the formal parameter and drag it into whatever you need to use it. So now this is going to iterate through all the salaries. What am I doing? Well, I'm probably adding something to the answer. And then we're going to be reporting the answer. I'm almost done here. So this is kind of the way we write this little for loop. And what am I doing? Well, I need to query this. So I need to I need to use salary somehow. So I need to multiply this by 2. So maybe we'll make a double block. Let's make a double block very quickly here. So I go here and make a double block, and double takes a number, and it's going to return the double of that. So returns n plus n, let's just say. Let's just do that here. So returns n plus n. All right, so I apply this and say, okay, I've got a double block. I can grab it here and just test it quickly. Here's my double block. I'll put it right here. I'm going to double 10. If I value is 10, I return 20. So I'm going to add double of this salary to salaries. Sorry, double this to the answer. And we can even do this. We can even do this better. Let's call this doubled salaries. So I can rename this. I re-choose this, doubled salaries. I then re-drag this down to answer. I know that is my answer. I'm going to report this guy, and I'm going to drag this out, and I'm going to drag this guy out. And now this kind of reads better. I feel a bit better in my, there we go. Okay, so let's see if this reads right. So first I created a variable doubled salaries. I set that to be the empty list. For each of the salary of salaries, the input, remember this is our salary 1 to 10, I'm going to add this doubled value to doubled salaries and report this. If I say apply, and now I go grab my double salaries, which is at the bottom of this new thing here, doubled salaries. And now let's put in the salaries here. One way you can do this, by the way, is you can tell Snap that this value should be a list. And so what happens when you do this is you apply as the now input type changes. So now this has it's just kind of reminding you visually this should be a list here. It's kind of a way, it's not formally, it's not strongly typed, but it just gives you a little hint with these icons. So I'll drop this in here, and now I'm hoping we should get the value 2, 4, and 20. And ta-da! I've now gotten 2, 4, and 20. So I've doubled the salaries. And so this is the solution most students write. And I say, that's nice. I don't mind that solution. We can keep it here. But can you do any better? And the students say, whoa, I don't know if I can do any better. I mean, there's an even more inefficient solution where I grab, a for loop and I iterate through this with an index variable. And this is a little cleaner with the for each that many people have in many languages. And I say, can you do any better? And they say, well, I don't know how I can do any better. I mean, that's pretty close to the optimal way, right? In fact, I've even had a teacher say, how about in 2? Haha, no, just kidding. And I want to say, why couldn't you do it in two lines? I said, well, it's impossible. Here's 5 lines. How are you going to, you're basically doing each line is doing what it needs to do. And there's no way to collapse this at all. I say, really? How about this in 1 line? I say, what do you mean 1 line? Well, this is a wonderful block called map, because map is going to do the work for me of mapping over, map handles the iteration. So I'm going to pass in the function I'm going to be mapping, using mapping over every element. Here I'm passing this in. This doesn't say to call double right now. This says to pass in the double function to the map procedure. Map them is going to return a block in which this function is applied to every element of salaries. So we can try this. I can say apply. And now let's try it again and see if our new doubled salaries works. And you notice now I've reduced this to 1 line. And so students say, whoa, this is crazy. I mean, I get this, but this is much easier. Tell me more. Tell me more. So then we talk about how we can use filter as well. So here's my list, and I can filter things. So I can filter elements that don't satisfy some values. So I can say filter the elements that are all less than 10. Map and keep, as you keep or filter, use monadic functions as their input. So these are inputs of 1 element of 1 input. So there's the 1 input there. So it's saying pick all the values from this list that are less than 10. And so it basically filters away the 10 because 10 doesn't satisfy being less than 10. Combine is the classic kind of combiner block, the last stage you usually do in one of these flat map and reduce. It's a kind of reduce operation. So I can do a reduce of this list. I can reduce this guy over different parameters. I can say, what if I want to add these guys up? And so part of the way we teach combine, this particular version of combine is right associative. So it's pairing up these guys I'll just add another one just to make it interesting. It's pairing up these guys. First is taking the right 2, 10 to the 100. This is taking a dyadic function. So it's taking a function of 2 arguments. It's taking 10 and 100, passing into the 2 elements, giving you a value. And that value then gets passed into the right element again. And then 2 comes in here as the left element. So it's 2 and then 110. That's going to be 112. And then 112 goes into the right value, and then 1 here. But we tell our students, you shouldn't know how combine works. That's below your abstraction barrier. So if I decide to rewrite combine as left associative, your operator, your combine should still work. And so as long as this dyadic function is associative, that is, regardless of how you parenthesize this operation, it should still work. And so we make sure that it doesn't have to be commutative. You can flip this. I mean, certainly combine. I can do a join here as another option, or join where I smush these guys together. So I'll show you this working here with the 113, as you guessed, add them all up, and that just works to 113. But join is a nice one where I smush things together. I can say hello world. So I can go to take this away, and I can click over here. Sig HPC, hello Sig HPC, and so I can put this, I put a couple spaces in the middle here, and I can say hello, and this just smushes those things together. So if I were to do this, pass this in as a dyadic function, let me leave 2 blanks here. Maybe put a comma. Maybe you like comma separated value files, and so here's a list of values. I need to then comma separate them. So if I take this away, I can pass this in. Now you notice that join is certainly not commutative. When I return this, I get 1, 2, 10, 100, and that's because regardless of how I parenthesize this, it's going to have the left to right ordering of 1 to 100. But certainly, it's not flipping these. So this is, again, a case of being a commutative, associative but not commutative operation. So combine works to slash these together, and you can write your own. And so you'll notice, by the way, I didn't have to make the comma block. You know, I could say, ooh, comma separate these guys. So I can make a block saying comma separate left. Pass this in, make it a reporter, and I can do this, and I can say report what? Well, I'm reporting the join block. I can put this in here, and that's going to then take the left and the right, and I can do this. This is not what I had to do to call that. So here's my comma separate block, and to test, you can see that I can say 1 and 2, and if I do this, you'll see that it's 1 comma 2. So I could pass this into this block as a blank block that has 2 inputs. Here's my there, and notice this does the same thing. But notice I didn't have to do this. I was able to make an anonymous function. This is the lambda. People who are familiar with functional programming know that lambda is the way we talk about having kind of anonymous functions. You can make a lambda in Scheme and in Lisp and that kind of family of languages, and Python as well. So this just worked. You notice this just worked, and this is beautiful. And part of the reason this worked is because this is really, we think of Snap as being, you know, if Scratch and Lisp come together, had a baby, because this is really Scheme under the hood. You know, we see many of the list operators are, this is a list operator, but I see this blank in front of list, and so I'll leave it to those of you who are, so if I pass in a list, I want to put something in front of that. So let's duplicate this guy and put, say, 0 in front of this. Whoops, put 0 in front of this. You'll see it just puts prepend 0 in front of the list. And those of you who are come from a functional programming background recognize this, or at least the list background recognize this as cons. This is the cons block. So really, what you're seeing is a graphic representation of many of the cons items. All but first is cooter. So item 1 of this is car. So those of you who are familiar with the kind of, this is kind of the Lisp vernacular for how to do those things, you can see that the many of these are still present in this graphical language, but the kids don't need to know this. It's called car and cooter. I always thought that was a terrible name for it anyway. So now this is done the right way. Item 1 is your car, your first element, and but first says that all but first is 2, 10, and 100. So this is the cooter. So because we have this kind of functional style to things, we said it doesn't make sense to just stop and not bring the functional ideas of map, keep, and combine, or map, filter, and reduce, however you think of it. Map is pretty universal. There's a single map, but people either call this keep or filter. People either call this combine or reduce. So the idea that making this lambda function is pretty powerful. But you might say to me, Dan, what if I want to do something where I swap these elements? You know, lambda of x and y, where it's y comma x. Well, you can't do that, can you? Well, maybe you can if I let you click this right arrow and let you name these variables. So here's your left and here's your right. And if I do this, here's my right here. And what if now I have to drag these over. And so now this is exactly lambda of left and right. And now I can use them. Here's my body. So this is just a way to do a more generic lambda in this Snap version. If you do this, you can kind of see if you can guess what the answer that might be as I do this. By the way, if I'm not going to use the stage, I can make this smaller to give it more scripting room here. And this is the beautiful reversing tool. So what's nice about this is, again, independent of how I decide to pair these guys up, I'll always be flipping these into a reverse of this order. It's just very beautiful of that. So 10 and 100 come in, they get flipped, 10 to 100. Then that comes in as the right element. There's the right element, which then gets put over here. So it's 10, 100, and then 2 gets the left. So it's 10, 100, 2. And you can see why this flips things. So this really powerful idea of keep and combine and map allows us to think about these in a functional way. And here's the beauty of this. I could make Snap, this happens to be Snap version. What's my Snap version? If I Snap version 4.091. If Snap version 4.092 happened to, rather than compute this locally, send this to a cluster with the environment and the closure around it, compute that value, and then come back. What if this list were not 4 elements long, but 2 billion elements long? Well, I might need to have some help then. my single core, in a browser machine might choke on that. So I send it across to a cluster, and I get back the simple number of, it might be, the sum of that, I get the number of all the first billion primes, say. So what's beautiful about this is I don't need to know how this works. This could, in theory, using this style, this could, in theory, go and perform a computation on a cluster. So we're in conversations with folks who are thinking about maybe having us do this and having this package up the Snap environment with its closures, pass it over to a cluster and come back and do that. And that's really delightful. So that's a kind of a demo of map combine, anonymous functions, and functions as data, kind of really powerful ideas within the HPC paradigm. Now let me go back and jump back into my slide deck because I want to show a couple more things that we share. I even have a full concurrency lecture I'm happy to kind of slide deck show through. So let me maybe do that actually. I did have a slide here set up here. Here's a concurrency lecture. So let me kind of jump this and make this full screen. So we have a dedicated full hour where we talk about concurrency issues. This is, we do some definitions of things happening in concurrent time. Let me pause this. If I pause this, it won't auto play. We talk about kind of two models of this. Either you have kind of the internal, we call them kind of an intra-computer parallelism and inter-computer parallelism, the grid and cluster computing. So having these be different. Today we're going to talk about, in this lecture, we talk about intra or multi-core computing. We talk about the von Neumann architecture. We talk about what's inside a processor. Here's a little Moore's law. We're reminding them, we just did a algorithm analysis. So we asked them what this curve is, if it's linear on a log plot. Then we talk about, again, these why there's why the sea change occurred. We talk about the history of this curve, and the why comes in when we talk about the power density issue. These are slides borrowed from lots of different sources. We talked about how the processors, we basically couldn't cool the processors down. You had a mini nuclear reactor on your laptop, and so we had to go parallel, and then talk very briefly about threads and how we can kind of time share across them. We bring in Amdahl's law to mention how there is some limitation to how fast we could ever go if we had an infinite number of helpers with us. We talk about some of the reasons that Amdahl's law exists. Here are some of the reasons we don't ever get to Amdahl's law limit. And the overhead to do these things of dividing the problem up, handing them out, not all workers being equally fast, the time it takes to bring them all together, etc. The sea change to multi-core parallelism means that computing community had to rethink so many of these things. So the answer is here, all the above in many cases. And then we talk about some issues of what happens at ATMs if my wife and I at ATM decided to run this block of code. So imagine if the ATM were running this and my wife and I both try to withdraw. So the balance, let's say, is 100 here, and we both try to withdraw $75 from us, from our account. And the students, get a sense, oh, this is code they know how to read. And both of them have this query where this test passed simultaneously, and then they get to this and the balance gets set to 25 for both of us. Both of us set the balance to 25 and the block retorts true for both of us. And we both got our money out of the ATM, and yet the ATM balance still reads 25, and yet we both got 75 out of a $100 account. So we talk about how the fact that Snap doesn't let two of these things run at once at any point. Snap is inside of a JavaScript window, and so it's single-threaded. There's no issue with that. We talk about non-determinism with parallel code, so things happen out of order, and that's a problem. But again, this doesn't happen with Snap, which is nice. People typically show, the Python multiprocessing rule, kind of the multiprocessing hello world is that you have it print out, hi, my name is number 3, and notice it doesn't count from 1 to 10. It reports in different orders when I run it differently. So that's often a neat thing to show, but also a challenge, obviously, a challenge to do that. To write code that makes sense, is debugged, that runs out of order. So what we do is we actually explicitly add this out of order to Snap in a fun way by having different numbers of weights. So we kind of talk about how race conditions can come up here. So here's, I want to draw a left eye, a right eye, and a mouth, but I happen to have in the world of Snap, you can have these event starter, these are called hat blocks. So when the green flag is clicked, these things all get run. Well, if each of them waits a random amount of time, all of a sudden I'm kind of forcing this non-determinism into the code. And each of them, because it's a buggy piece of code, is going to clear the screen, because we decided to copy, clear, draw left, clear, draw right, and cleared the mouth. And I ask, how many different outputs do we have? This is kind of an easy, gentle way of introducing this non-determinism into this. And it is the case, if I were to run this program, you'd see this guy show different pictures. Sometimes his left eye comes out, sometimes his right eye, sometimes just his eyes, sometimes all three of them, depending on the values of these random variables as these guys get set. So it's really quite an interesting way to explicitly do that. So we can talk about this principle without having them at any point when they go to run this. If they don't explicitly do this and have an explicit weights in there, that'll never bite them, which is nice, because these are, you know, first-time programmers. You don't want to have these issues be in there. And I'm sure you saw the Snap is has multiple sprites. So if I drag this window bigger, you'll see that there are multiple sprites. I can add more sprites to this. So this is the idea that each of these sprites could be doing things and could be changing some state of the program. And within each of these sprites, I can have these event starter guys, like when this is clicked, when this is clicked. Well, let's do something. Let's try to create that together. Let's make a variable called a balance. So here's my balance, right? Here's my account balancer. I don't know why I call it balancer, but this guy is it's set to 0. So this person is gonna change. This one here. Let's set balance to be balancer to be let's see, balancer plus something else. Let's do a quickie thing. This will never cause a trouble. Let's see, this is going to double the balance, right? So this is double the balance here, right? Here's this, and this is going to do set balance to some other thing. Let's see what this guy's going to do. He's going to set balance to be, and let's relabel this to be 2 plus balance, right? So make this a 10, just a little different, okay? So obviously balance will get a different value if I both double it and add 10 to it. If it starts at 0 here, if I double it first, that's again 0, and add 10, it'll be 10. If this goes first, it'll be 10, which I double to be 20. So when I actually launch this, there'll be a predictable output to this. So let me now reset this, and I'll just show you what that is. So if I go here and I set balance to 0, balancer to 0, sorry, you can't rename these yet. Excuse me. So if I run this, I click this, it gets 10. And 10 says this runs first than this. Let's reset this to 0. Reset this to 0 again. And notice if I run it again, boop, it's always 10. There's no question about this confusing students, because they did have a race condition here, but there's a predictable order to these things, and these things aren't going to come out of order. So this may be unpredictable to them, in which they don't know that, oh wow, this is a race condition, but it won't give trouble in terms of every time it might give a different value. So the non-determinism isn't there, but the unpredictability might be there if they do have these race conditions. And you also have multiple sprites doing things, maybe changing internal states. So this is and by the way, this all we inherit this all from scratch. So this parallelism comes from scratch, and kids in grade school and middle school are using Scratch with these blocks in their code and multiple sprites, and somehow they're able to handle it, again, because Scratch has this kind of single-threaded approach where nothing is non-deterministic unless they kind of force it with some weights in there. But the point is, there is this, kids kind of just get it. Kids at this young level are getting the idea that multiple things are happening at the same time. You know, one of these guys could be making this go forward. One of these guys could be making it turn. And then what you get is, if one is supposed to just turn in place, is a beautiful example of why kids do use this. Just as an example here, I'm going to do a forever loop here, which is really beautiful. So let's get a forever loop. And we're looking at what sprite? The blue sprite, which is the bottom right. So this forever loop is going to do it twice, and this forever loop is going to move forward. So this forever loop is just going to move forward by 1 step. So let's go do that. Let's go do that 1 step, and this guy is going to turn by 1 degree. Okay. So normally, if I just ran this, and here's the blue guy, so I can do this here. I can delete those other sprites. We don't need those guys, because I'm just talking about the blue guy here. And you guys all seen this. I don't need to go back to that. So here's the blue sprite here. And so now I can even make this a little bit bigger, because I do care about what the screen looks like here. So I'm looking at this, and here's my wonderful sprite. If I just do this guy, he's just going to spin, okay? And I stop him running. If I just do this, he's just going to start moving. But when I do both at the same time, I get this beautiful circle pattern. So there's no trouble here. There's no conflict here. I'm doing both at once. I can draw a pen, I can drop the pen down, and I can draw this pretty blue circle. So the idea is kids are doing these kind of things, these kind of really nice things where multiple things will happen, but it's not multiple things that they explicitly wanted both of them to happen in that way. So it's not like, whoa, I wanted to set some balance of some bank account and I'm confused why it's not 20, why it is 10. Kids do these kind of things with their multiple sprites. So let me jump back into here. So this is an example of kind of the question we're asking. We actually do explicitly. We talk about deadlock with this beautiful picture of a deadlock in traffic in China, of when two people are trying to do this. This is the dining philosophers. We're just kind of introducing this. Remember, these are non-majors here, so they're getting a little taste of some of the principles and some of the gotchas that happen when we're kind of moving concurrently. So we talk about this, the sea change happening. We do this. We also have a delightful guest lecture by Professor Kathy Yellick, who comes in and talks about how she saves the world of computing. She's the director of computing sciences at Lawrence Berkeley National Laboratory. So she comes in and talks about some of the things they're using their massive clusters for. So they talk about climate change simulations and digital body simulations for medical purposes, that kind of thing. So I did mention that this is bringing these HPC ideas worldwide. This is the slide that talks about that. So we did launch an edX course. We have 16,000 students in 140 countries, I believe. We did a global launch last year, fall and spring of 15-16, and we're relaunching that again fall of 16, spring of 17. So that's great. We're also passing this again. This is in the service of supporting high school teachers, really, because we want the CS Principles course to be successful. We do care that we teach some kid, in a basement in another country, but we do care also really primarily are driven by the desire to bring computing to kids in inner cities and kids who are not getting it across this country. So the idea is, and this is Armando Fox coined this term, a SPOC, small private online course. The idea that you take a MOOC and all the resources poured into them, auto grading, quizzes, reading assignments, videos, and you hand that to a high school teacher or to another university professor who wants to use that as a resource in their class in the context of a small private online course. So it's kind of like an ebook in some sense, where this teacher or instructor gets to use the resources as they want to. Part of the thing I always highlight is they can pick the parts they want. They can mute things, just as any instructor might want to say, all right, students, do all the odd problems in the back of the book. This, the instructor here in a MOOC can say, I don't like the presentation of this material, or that's V is really fun to do myself, so I'll mute the little subsection where I introduce V on the video, and then I'll be able to, as the instructor, do V live in front of class. It's always fun to do V where they get to see the parallelism. I should just show you V because V is such a delight, just because I feel almost remiss if I don't just give you a V. V comes with Snap, by the way. If you want to get to V, you go to the examples, you choose V, and you grab it here quick, and it's going to then load V. And here is the shapes. It's now V, again, moves to the left, picks one of these ends, moves to the right, picks another end. I'll just show this in less than a minute. And every time I run this, it chooses it randomly. Again, it's picking this randomly. And if I hit spacebar, here's the code for V. I believe I can full screen this here. So you notice that nothing's really interesting. It's just kind of randomly picking these guys and it's doing this. But if I then have up arrow and I add V itself, and I have to usually turn my echo on, V itself, self to the demo, then what happens, and you then get this beautiful these beautiful trees that are different every time. Certainly there's some randomness to this, and V could take a long time to run. And so it's really delightful to do this demo in front of class to show them the power and beauty of recursion, how simple this is. And here it's elegantly handling the base case by probabilistically not choosing V at the terminal points here. So this is, again, this demo is only made possible by the fact that it's really easy to choose to have functions be data and functions at first class. Here's an aggregate list of them. That's the only reason that's so exciting to do. So again, Kathy Yellick comes in at the end talking about distributed computing. She doesn't really talk about the details of it. She talks about more of the application. So it's application, 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 each one of them born by the use of having this cluster of resources at her disposal and at the team's disposal, at the researcher's disposal. In summary, I'm giving a little bit of time for questions. I'm 5 minutes before the end. Beauty and Joy Computing, a CS Principles course, is a CS Principles course that allows, so CS Principles is this framework that allows for many interesting courses to kind of, to flowers to bloom. BJC is one of those flowers. It takes a more programming heavy approach toward programming, toward the kind of the programming and abstraction and algorithms concepts. We emphasize a couple big ideas that are part of the SIG HPC family. Functional paradigm, program procedures as data. Procedures is a general class of both commands and reporters, both things that have side effects, commands, and have no side effects, the functions. Map, keep, and combine are certainly part of any part of the toolbox that anybody who's doing big data is going to be using in a functional technique. We talk about concurrency and some really early basics, distributed computing in Kathy Yellick's lecture. And again, this CS Principles MOOC is the way we're kind of sharing this with the high school teachers as a SPOC, but also with the world as a MOOC. And if you're interested, the course is running right now. Feel free to pop in and look at some of our lectures. The link for that is bjc.link/bjc@x. And with that, I conclude and allow for a couple of minutes for questions and a couple of minutes to allow folks to digest it all. So thank you for the presentation. Thank you for the honor. I'll go back to the window and on screen share. I hope that was useful to folks. Lots of fun to give. We've been going around the country talking with high school teachers who might be adopting this program, this course. We've also been in conversation with other folks who believe that more HPC ideas should be integrated into these courses. And remember, we're just one flavor, and we added it, but not because we're told to add it, because we love to add it. So there's a subgroup of us who believes that we should bring HPC ideas into the curriculum framework, and that would mean once it's in the framework, then it gets taught by more universities because it's required. Then once it's the framework, it's now on the exam. None of the things I showed you are on the exam because they're kind of we call that the BJC secret sauce. So the things above and beyond the CS principles that we do. But those of us who believe it should be on the curriculum framework, if we can get it there, then it's certainly required, and we'll get a more play nationwide. So there's a potential that this goes beyond BJC if we can get into the framework.
So if you have questions, this is the time to post them to the Ajax chat, which I have again up on the screen. And so we'll wait a few minutes. There is a time delay between the broadcast and, okay, what age groups of students do you normally work with? Is it mostly upperclassmen in high school or freshmen?
Oh, perfect. Wonderful. So when it's taught in the high schools, it's typically 11th and 12th graders. Sometimes a precocious 10th grader will come on in. That's a very good question, by the way. And for our non-majors course, by the way, many other universities are borrowing this BJC course and using this as a framework of what they do. So Tiffany Barnes uses it at NC State, and other folks have done that as well. Earlham, I believe, and some other schools. At those non-majors courses, it's you're welcoming the entire campus. So I've had grad students come in to take the course and have been very interested in those grad students from English and from German and from chemistry, folks who haven't necessarily had any formal computing. So it's welcome to everybody. We love when freshmen come in because then we can change their minds. Then we can bring them into the computer science. Not that we need any more CS people, but certainly bring in the folks who come in who are freshmen and sophomores who come in to our non-majors course and then eventually flow their way into the majors. They bring more diversity. You find more diversity in terms of both gender and ethnic diversity from that kind of pool of students than you do from the traditional pool of students who knows that they want to be a CS person since they were 5 because their parent gave them a computer and they've had it in their basement. That is a very non-diverse pool. So we bring more diversity in by trying to grab the freshmen and sophomores. But again, our course welcomes everybody, and we have folks from freshman to senior. In fact, it's really a shame is I get so many seniors who hear about it too late, come to me and say, Dan, this course is amazing. I wish I would introduce to this earlier. I would have changed majors, but I'm already, I'm a senior now and it's too late. So, but I hear that too often. So I try to get the word out so that people don't have that happen to them. So
let me note that the chat area is acting flaky this afternoon. So the fallback was to send an email to gordon.1@osu.edu if the chat window is not working. seems to be going in and out. I'm not sure why. And I will complain to ACM, who it's running on their server, but I have no idea what's going on this afternoon. So,
yeah. Oh, and thank goodness we kept the Hangout link up. I don't know what went down. I didn't do anything different. I didn't hit a button on my end, and I'm wired, so I don't know what happened. But somehow we lost the connection halfway through there.
Yeah.
So
well, I will edit out that pause when we.
Oh, thank you for that. Yeah, I didn't know if that's easy to do in post. Yeah, that's great.
Yeah. So let me just check my email to see if I got an email.
Sure.
Any email questions? Not so far, but anyways, if the chat doesn't work, please send an email to gordon.1@osu.edu.
Sure.
We'll wait a couple
minutes. I can talk a little bit about other flavors of CS principles. So the many other folks are out there, curriculum developers who are saying, this is a great idea. Let me take my course and bring it there. So some of the more kind of I would say famous, the ones who've gotten some NSF funding and got some publicity are Mobile CSP. Ralph Morelli out of Trinity College in Connecticut has a mobile computing based on App Inventor. So they don't do some of the HPC things, but they focus a lot on, how do you build a mobile app and how do you use that to collect data, which really connects in with the big idea too of data, to allow the students to go out, build an app, and then go out into the field and collect data and then bring it back and then process it. That's a nice thing. There are folks at University of Texas who have a course called Computing in the Digital World, and that really brings in the computing plus X angle. So they really they have a wonderful ebook in which they're bringing in, computing is nice, but look how computing can affect all these other disciplines. That's their angle there. Other folks are coming in. There's a Swift programming, so focusing on mobile apps on iOS devices. CS50 is a course out of Harvard, which is another CS Principles initiative. I'm almost remiss in not mentioning Code.org, which is really the elephant in the room, the big one. They're reaching many more CS Principles teachers than possibly all of us combined, and they have a really broad. I'm not sure if I want to put a label on what they do, but they end up building apps at the end using a really beautiful and elegant application, an in-browser application. So
we had actually talked by them our last webinar was by them. So
beautiful. Yeah, the Code Studio, I believe. I just remember the name. There, it's delightful. So they were talking about CS Principles. I'm not sure, but Code.org does a lot of things, and so one of their things that they do is their kind of junior level CS Principles course. And so they've done a great job with that to try to get that out. There's a lot of teachers doing Code.org across the country as well.
Well, I haven't gotten any other emails, and I can't get the chat to start again. So, unfortunately, if people have any questions post presentation, you can send them along to me, and I will pass them on to Dan, and we'll try to figure out a way to distribute them, distribute the answers. So, Dan, let me thank you again for making this presentation. We very much appreciate it. And for those that are listening, I will be, if you missed part of it, I will be editing the video over the next couple of days and posting it on YouTube, and I will have a link to that on the chapter website. So thank you again, Dan. I very much appreciate it.
My pleasure. My pleasure. I really enjoyed it. Nice meeting you all virtually.
Okay. Bye now.
All right. Take care, bro.